Is Amanjot Singh, and I'm a senior engineer water quality with Credit Valley Conservation. Have been with the organization since 2008. Love working here. Love my colleagues and especially my team. They're all awesome. They make my life easy, and also because of them, I look good when I'm presenting somewhere because they are all fantastic people. So I'll be your MC today, and when I was looking at we always hear about these acronyms, MCs and DJs, and also we don't know what it means, right? So I was saying, I was okay. You know what? Let me Google what the MC means. And it says Master of Ceremonies. I said, wow, that's a cool portfolio to have, right? So, anyways, so the agenda will be tight and as well as like interactive. So I will walk you through some of the things which we'll be doing today. To start with, this is the agenda. I don't know about the rest of the people who are attending this workshop in person or not, but I am really waiting for coffee to come. So once it's here, so I'll be probably a little bit more awake than I am now. But we'll start, I'll be doing an opening remark. So, and walk you through that how often do we do these type of workshop, just not to, or I would say to make sure that the work which we are doing here, people are aware, and we love to collaborate and love to, extend partnerships with others. And we want that, this work which we are doing here is also useful for others in a broader schema, right? So I'll talk about that. And then, we'll talk about the two tools which we have developed with this grant. How do they work? Why we wanted to develop them, and what is their use? And then we'll have a question answer session, and then the second tool will kick in. And a part of this project, we also did some new investigative things using the drones, using the lidar sensor and the multispectral sensor, which is going to be the cutting edge in this science which we are working on, especially when our interest is to reduce nutrients or reduce sediments from actual sources. Yeah, we do modeling stuff. We do lots of modeling here too, but it to translate into actual management practices and restoration, you need to go to the actual fields and see how the things are and where it will give us the most of the benefits as the sediments are released. So we'll talk about those, and there will be question answer session at the end, and hopefully lunch will be coming too on time, and we'll do some question answering during that time, and while we'll be enjoying the lunch. So to start with, some of the housekeeping notes for those who are attending in person. There's one washroom which is gender neutral, so you can use it. It's just across. But if it is somebody's already using it, there are two washrooms down on the main floor. So please feel free to use them as needed. If in case the fire alarm rings, don't follow me. I'm just kidding. So there are exits. Just follow those exits, and somebody within our team will be leading everybody to go out. Hopefully that doesn't happen, but it happens when you are not expecting it to. So let's be sure that it's working. Oh, camera is not on. Uh-oh. Various teams right here. Okay, right here. All right. Window again, and this one again, and oh, sorry, folks, you were the camera was not on, so you are not able to see me. The purpose is that you also see the speaker when we are doing the presentation. So Okay, so I was here. I'll request, please, for those who are here, put your cell phones on silent. And again, I'm waiting for the coffee and some cookies to come with. Hopefully, they will be here soon. For those who are attending remotely, thanks for joining us. Um, uh, on your screen, you will see this Q&A button there. So if you have any questions, please populate or put your question right there so that we will bring your questions during the question and answer sessions. Um, so what I'm doing here is we'll keep our questions until end of the presentation, right? So we are not taking any questions in between, so that everything is addressed at the end. And of course, please keep your camera off and also your mic off. Um, and the workshop will be recorded or is being recorded, and the links will be shared on all the platforms. So we'll be sending the link to all the participants, but on top of that, it will be on CVC's website and also shared through LinkedIn and other places. So, yep, that will be available. Um, so I'll start with with a little bit of introduction on where we are. So, like I said, that I work for Credit Valley Conservation Authority, and we are hosting this workshop in our boardroom, which is beautiful. Those who are attending online, next time, come make an effort. Come here; it's beautiful, right? So, and Credit Valley Conservation Authority is one of the 36 conservation authorities in Ontario. We are located, our head office is located in Mississauga, but we go all the way, our watershed goes all the way up from Orangeville down to Mississauga. It's the river itself, just itself is about 100 kilometers, and the watershed is around 1,000 square kilometers. So it's beautifully laid out, and we have some major municipalities starting from Orangeville, Caledon, Erin, Halton Hills, Brampton, Mississauga, which cover this. But along with that, I wanted to introduce you folks to the real-time water quality program, which I lead, and I have, like I mentioned earlier, I have a very strong and energetic team here who really support these type of initiatives. And what we do, and this program actually started in 2008 when we got, climate change funding from Region of Peel. This project initiated, and the main purpose was to do to monitor water quality, and we were to do it using some kind of real-time mechanism. And I was hired because of this new grant which we had received. And then we started to develop this network. At the moment, we have 11 stations across our watershed which collect key water quality indicator parameters every 15 minutes round the year. And that includes not only just the standard parameters, but it includes turbidity, then dissolved oxygen, chlorides, conductivity, pH, and all the stations have either the flow stations or the water level stations there. And we also record air temperature at all the sites to make use of it. And all the data is posted at this particular website, and it's open to public. And this is something which you will see on the website, and I am going to focus on this my interesting thing, which is always chloride. You see for this particular station how high the chloride levels are. They are kind of they went up to 18,000 milligrams per liter, where our peak objectives are our guidelines are 640. So you can imagine how high the chloride levels go when there is a spring freshet, and how it is impacting our streams. Then I always share some of the key things which we have noticed from our real-time stations. This was one time in 2012 when I was getting alarms. So we have alarms at all the stations that if any of the parameter goes off the limits, then we'll get an alarm and we'll see that what's the reason for that. And this was happening for the dissolved oxygen in one of our urban creeks, where I was getting alarmed early in the morning, the levels to be around 2 milligrams per liter. And when I was coming back to the office, I could see the levels to be 14 milligrams per liter. I said, what's going on? That's something which is not usual. Then we all went out, and this was the situation of that creek. You see how much algae was there, right? So, and it's typical that during nighttime, this algae will suck out all the oxygen from the water body, but during the daytime, the photosynthesis triggers, and it releases tons of oxygen, right? But this was then, associated because it happened in May. All the urban creeks have algae issues, but we have never seen to this extent and this early on. And it was triggered mainly because the 2011-2012 winter was really mild winter. There was no snow, no spring freshet, and the temperatures were going up. There was not much rainfall in the spring. So it was a perfect recipe that sediments and nutrients were there in the stream. And the temperatures were conducive, and there were huge blooms. And at that time, I called one of my colleagues at Region of Peel to see that what's the situation at Region of Peel. Same thing happened. They had lots of issues at the drinking water plant, where this algae was growing and being sucked at the inlets, and their screens were getting filled with the algae. Thanks, Lorna. And so those are the things which, again, if we are really interested in knowing what climate change can, it's not going to happen everywhere, but this is something where we need to wrap our heads around that these are the type of recipes which will really be of concern for us, not only for recreational purposes but also for drinking purposes and aquatic life. I mentioned about the chloride levels. We have seen chloride levels which were above the sea level chloride level. So that's again which you don't see if you just go and grab water sample and give it to the lab. But if you have the continuous monitoring system, that's what you observe in there. And also, this dates me a bit. Here you will be saying this is an ice cream maker, and it was very. At that time that, if you really want to make an ice cream, you put the ice in the outer skirt of the ice cream maker, and then you pour lots of salt in that, and that brings the temperature down, right, below freezing, and it quickly makes the ice cream. That's exactly what was happening. I was looking at the water temperature in one of the creeks during spring melt, and the temperature was minus 1.1. First was shocking. How can water temperature go below 1 degree? This is the reason, right? So again, something to understand that how these things can impact our ecology and aquatic life. This is important to understand. We do some so 4 main stations. We have 3 stations close to one station for the Credit River close to the to its mouth, and there are 2 major urban creeks, Cooksville Creek and Sheridan Creek, which are again discharging to Lake Ontario, and one up north, which is downstream of Orangeville, where we have cameras installed to capture that, means what's happening. In case a spill happens, then we are able to look at those cameras and see what we are getting. So we get alarms from our real-time stations, but then we can visually see through our cameras that what type of spill is going on. And this is something which we wanted to understand during the winter period into the springtime. That how the spring during spring period or during winter period snow accumulates, and how it reflects to the chloride levels and the water temperature in the river, and what happens, how quickly it recedes, right? Again, informing science, informing where are the critical issues, and I'll show you why these type of things are really important. So we do lots of modeling, and I would say that our modeling team again is using a cutting edge tool, which is Mike Shee model. This is the DHI, which is Danish Hydrological Institute, developed it. It's a very physical based model. It's fine. It uses finite difference. Those who are familiar with mathematics, and we use grid size of 50 meters by 50 meter, and we have set up these models for all of our 22 sub watersheds, and that's how we are trying to understand water balance, how it looks, trying to see that how much sediments or TSS and TP gets released from that. So, and the beauty of this model is that it is integrated model, which talks about surface, weather zone, and also groundwater. So we have 13 groundwaters which we borrowed from our source water folks, and we have put them in our model. So it's a phenomenal. It's growing. Still, we are working on that, and I would be happy to share that I just got $200,000 grant from the province, which is under the COA project, where we'll be studying it even further, that how the TSS and TP, the total sediment solids and total phosphorus, is getting released. Where are the critical subwatershed which are more contributing, and how the management practices can help us mitigate that. This will be also running it on one of the climate change scenario, just to see that what the climate change impact may be there. This is again one of my favorite videos. This was done way back, I think 2012 or 2013, but showing when a storm event comes, when the total phosphorus plume is coming through the Credit River, how does it land into Lake Ontario? Just to remind you, in our jurisdiction, we have two regional Peel drinking water intakes, and we have two wastewater outfalls in the lake, right? So that's how critical our near shore is, right? So that's what we wanted to understand, that you will see that this part is Lake Ontario. This is where the Credit River is coming to the Lake Ontario, and this is showing one of the events. And if I share with you, this is how the plume goes, and within that particular event, because of the localized wind, that how far the total phosphorus can go. So it's important for total phosphorus, which we did, but we also will be doing it for E. coli, because that's another thing which is very important to understand. But again, these are the things, these are the tools which are helping and showing that okay, means these plumes can go either way during a storm event, can impact our drinking water intakes, both from sediments and phosphorus and also from E. coli stuff, right? So that's what we did. Now we are expanding our work. We got into cyanobacteria studies a couple of years back, when one of our area municipalities indicated that the freshwater urban lake was experiencing cyanobacteria. The problem is, or I would say, during the COVID period, what happened was all these small lakes were so popular amongst local citizens of that area. But what happens is, if we see that cyanobacteria is there, then for rest of the season the lake is closed for recreational activities, because we don't know, because of the dynamic nature of cyanobacteria, how they can be at surface, at the bottom, or they can move because of their ability to float from one place to other. And once they release a toxin, that's where the problem comes in. Those are neurotoxins, can impact the dogs and wildlife and also humans, and it's a growing problem. So we did this study, the pilot study, with our partners. We got funding from, and also from University of Guelph. We got some funding. We did 2 years of monitoring, and if you guys saw at the beginning that we have a drone now, which has multi-spectral sensors, and we also launched our water quality sondes through this to understand that how things are, and I will show you later on. But this work is continuing, and we are applying for some additional funding. to continue this work to better understand the dynamics of cyanobacteria in our local freshwater lakes. We are also moving ahead with not just the traditional water quality sampling, but we are getting into more microbial analysis. Hopefully, this year we'll have a lab where we're at our CVC head office, where we'll have potential to use the digital PCR technology to isolate that what type of if it is E. coli, then what is the source of E. coli using the microbial source tracking, and if it is say cyanobacteria, then what species of cyanobacteria is there, or if it is different type of algae, that what type of algae is there, right? So I'm so excited about having this. It will be a good learning experience for us. But again, working with our municipalities, working with feds, working with the province, these are the issues which are real issues, and these are the technologies, whether it's a drone technology or it's the microbiology, where the science will actually tell us that what the sources are, and then we can, if we plug the sources, that will be the best benefit coming out of these studies. And this is, I just wanted to show and a little bit also brag about this, because this is what we got a beautiful DJI M600 drone, which is a huge drone from Region Appeal, and I always thank them for giving it to us. So what we were trying to do with this drone was to launch the water quality sound, and simultaneously use cameras, different cameras, to capture that what is how does the lake look when we are taking the samples or when we are dropping our water quality stones. So I'll play this and I'll show that how did it work. So this is going to Lake Ontario, and we did it up to 7 meters. So I'll just go back here and show. This is a water quality sound which was attached to the drone, and you see that this drone is carrying that and then launching it in the lake at about 7 meters depth. And while it is doing that, taking the reading, the whole profile, it's also capturing the thermal imaging and the visual imaging, right? So that's the beauty of what it is. And then what is it's showing us is we have the profile, the whole depth profile for that movement, right from the surface to 7 meters depth, or it can go to 15 meters depth, wherever you want. So this was more of like a trial study. But again, this is the information, especially if we are talking about cyanobacteria and this stuff, because of their dynamic buoyancy effects, they can move throughout the column of the lake, depending upon where the availability of nutrients is there. So that's where this type of technology, because it's minimum disturbance to the water column. On top of that, you are not that much concerned about the weather. You can launch, you can fly this big drone and have the profile at some of the important events that may be happening. And also, you don't have to send staff in the lake every time to get those readings. We also did a trial run for actually collecting a water sample using the same drone, and we were very successful. The only thing which we'll be modifying is that at the moment it was taking the sample, the composite sample, not the depth sample at a particular depth, but we'll be developing another sampler which will have a capacity to tell us that at what depth water sample was taken, so that we can analyze the whole profile, while we'll be also monitoring the other parameters which are important, right? So okay. Okay, so now we'll start with the actual fun stuff, which we started in December, I believe, and we are now kind of compiling all the results and the findings and the tools which we developed. And again, thanks to Canada Water Agency for funding this project. It came in a short time, and we were able to, I think we are in good shape to deliver all the deliverables, all the tasks which we intended to. So the basic thing was like means when I also sit on one of the Great Lakes Water Quality Climate Change Annex, so I'm involved in that type of work. So the main thing is that okay means what learning from again Lake Erie, whether it is or some other lakes or local lakes, that phosphorus is a concern, right? So this is assessment that okay, what targets should we keep for Lake Ontario? So this is from the binational report IGC's released it, okay, that there will be around 7,000 metric tons per year of phosphorus that will target, and the concentration should be around 10 micrograms per liter. But on top of that, like means if we want to achieve that, yes, you want to monitor that whether your target, your at least your concentration target is there or not. But what you need to do is monitor also the watersheds from where the input is coming from, and for that you need to do lots of monitoring and modeling, and that's what I showed you using whether it was a Mike Shee model or Mike 3 model or the real-time water quality network which we have. On top of that, we have also we take graph samples every month around the year for all the parameters of concern which are used to calibrate these models and stuff, right? And then once those are done, then we will have is the estimate, right? So update the estimates of how much annual loading is concerned. So yeah, we are in the Credit River watershed. We are Credit Valley Conservation Authority. At least we can do it for the Credit River and develop some kind of techniques which others can also use. But again, the Credit River has been identified as one of the major contributors of total phosphorus to Lake Ontario in the Canadian side. So that was again the interest. But on top of that, when we have models, we have the estimates of the loads. Ultimately, what we want to do some restoration. We want to do some management practices so that we can cut down on these loads going to Lake Ontario. And that's what this project is focused on, just to identify what are the sources of Credit Valley of the phosphorus, so that we can look into different practices. And yeah, Hotspot Identification Tool, that's what it is. Hotspot for where the sediments and phosphorus can be released. And we started actually, we developed the first time just a conceptual thing in 2018. And we were trying to give it a name and acronym, right? So it was like Hotspot Identification Tool. That's why HIT is a good one. But we also wanted to add sediment there. So we had a good chat. And I'm so happy with my staff that the S should come in the front out at the end. So I love you folks, those who come with this idea, you make my day, right? So, and then we were also thinking, should we call this workshop as a HIT workshop or S in the front or at the end? So love it. And on top of, one more thing is like I said, that we have a modeling group here, and we have a modeling channel. And suddenly I see our modeling channel had a name on that, and that was Catwalk, the Catwalk. I said, modeling and catwalk, that makes sense. So again, all this humor is also coming, and that's what it is. Like if you're doing serious stuff, you have to bring the lighter stuff so that your mind opens and that you can work on that. Anyways, smaller things here. So how to identify and rank the hotspots is a key thing where we are focusing on. And if I look at the bigger picture, there are three main contributors which have some distinctive features which we need to understand before even when we identify those hotspots or rank them. One is urban areas, right? So urban areas, again, I was doing some study in 11 or 12, and I was presenting, and actually 2012, there was a big storm event, and in Coastal Creek, there was flooding, right? So why that flooding is happening. And we were saying that, okay, well, there is not enough, water quantity control, and that may be one of the reasons. And we are further investigating that why there was not enough water quantity or quality control. Just imagine this: the whole area was developed in 1950s. The only issue was that how quickly can we drain the area. You go to square one, literally it takes 15 minutes for a drop of rainwater to fall there, go to the storm sewer network, and go to Lake Ontario. 15 minutes. That's how quick it is. And I was saying how proud that drainage engineer would be that, created that network. But then we started to develop every part of that, right? And every part is releasing in 15 minutes. Flooding has to happen, right? So that's where you need to identify that, where the main sources are, where the impervious areas are, that will generate more runoff, will generate more sediments and sediment-bound contaminants so that we can control those. So the focus when we do, urban evaluation, it's based off like, what urban classes are there, whether it's institutional, high density residential, low density residential, or, there are plazas or whatever. And those are critical for evaluation because ultimately everything has to go to the storm sewer network and get transferred. But if we can do the source control using whether it's a low impact development, which are we are big promoters of that, and they really work if they are done correctly, right? Or we can have dry ponds, we can have wet ponds for water quality treatment. Those are necessary. So this is again concept behind the urban thing, and Lorna will speak more about it. And this is based off like event mean concentration that data collected for years and years. But when we jump to rural areas, it changes, right? So rural areas, especially during spring and winter period and post when there's no crop cover, the land is more dependent upon like what type of slope is there and what type of erodibility factor of that soil is. So we thought, okay, what? Let's combine these two things and see whether we can use another thing which is called SPI, the Stream Power Index. Can we generate those stream power index to identify the path of concentrated flows, whether coming from the farmlands or other lands, and we can rank them and then see that those are the areas where we should be using more of practices. Another important thing which we did not touch and we are still looking for, again, CWA folks, if you have funding, we'll love to work on this. This is in-stream mechanism of whether it's bank erosion or it is any kind of other sediment transportation. Huge, 40 to 60% of sediment is delivered through stream bank erosion, right? So it's a critical part to understand, and we need to learn more. These two pictures which I'm showing you, this is pre and post. It was the July event last year. How much erosion took place just from this one particular event, right? So it's phenomenal. So we need to understand more, and that's where the newer technology like flying drones with the LiDAR is going to help us understand that where are the critical points and bringing those data to our models to understand where the structures need to be reinforced or where the banks need to be more stabilized so that these things don't happen. So now is the time to introduce you folks to the main team members who worked on this project. Lorna, Murison, she's a coordinator real-time water quality, and we have them since 2013, I believe, 2012. And again, a very important part of our group, and she's into modeling and GIS and all the stuff. But I'm also good at, as some of my colleagues say, that stealing other staff members from other groups. So we have Andrew. He is in environment management, information management, and his GIS skills are awesome. So Lorna and him, they developed these tools, and they will take it from here. I'll invite Lorna to come on the dais and take it from here. Yeah.
Okay.
Sure.
So if everyone who came here in person our coffee and everything has arrived, so if you want to take a few minutes to grab some of that while I get set up, you can go ahead. Okay, I think we'll get started again. So I'm going to start by talking about some background information and overview of the concepts involved in what we're calling the urban tool. So brief review of our agenda today. I will go over an introduction overview of the urban tool. Then Andrew is going to do a demonstration of that. Then we'll break for a Q&A session about that half of the tool. And we'll repeat it again for the rural side of things, where I'll give some background and overview of the concepts. And then Andrew will give a demo, and we'll have another break for questions. And then come back to talk about some of this drone data collection in more detail. So underlying concepts of what we're calling the urban tool. So as Aman was just talking about, we know that the Credit River is a major contributor of total phosphorus to Lake Ontario. And we do have that real-time water quality monitoring station at the outlet of the Credit River, or very close to the mouth of the Credit River. And we are doing real-time water quality monitoring there, including turbidity. And you can see some of that turbidity data at the bottom of this slide. So we've used the data here along with some grab samples that were collected at the same location to create a relationship between real-time turbidity and total phosphorus and total suspended solids from those samples that were collected and sent to the lab. And you can see with the top graph on this slide that there's a strong relationship between real-time turbidity and total phosphorus. They increase together pretty much linearly, which is telling us that during high flows, a lot of that phosphorus that we're seeing in the credit is coming from the sediments that it is bound to. So because of this, we identified a need to prioritize areas on land that could be contributing a lot of sediment and thus phosphorus to Lake Ontario. So the tool we've developed is essentially a screening tool that's going to work at a high level to identify areas in the watershed that someone might want to investigate further in terms of implementing best management practices or further looking into what the sources of phosphorus might be. So when we consider sources of phosphorus in the Credit River watershed, we realized that different approaches would be needed for sub-watersheds that are dominated by urban versus rural land uses. In rural areas, it's driven by agricultural practices primarily, like Aman talked about. And in urban areas, we're really looking at stormwater runoff from the different land uses that are around upstream. So for the rural tool, we built on work that was initially done by the Grand River and Lower Trent conservation authorities, and they focused on stream power index and soil parameters to try and look at how soil areas that is in agricultural areas that are vulnerable to having soil loss. And then in urban areas, we took an event mean concentration approach. And use the simple method to estimate runoff, combining those two things together to estimate how much sediment and phosphorus might be contributed from different land uses. This work initially began in 2018. We developed and ran the methodology on 2 rural and 2 urban subwatersheds in the Credit River. This poster to my left is showing the results of our work back in 2018 on the East Credit River, which is one of our rural subwatersheds. And then, of course, we received funding to convert this workflow into an automated tool or a couple of automated tools. And the steps remain mostly the same as we did back in 2018, but with some adaptations to make it work in a automated ArcGIS environment. So what we're presenting today then is 2 ArcGIS tools that we have developed, one using this rural methodology and one using an urban methodology. We have also included in the package an existing ArcHydro tool that can be used to create some of the necessary input files. I'll go over that in some more detail as well. So to run the toolbox that we've provided, you will need an ArcGIS license, and the basic license is fine for this purpose, but you do need the spatial analyst extension. For the rural tool only, the urban one will work just fine with a regular ArcGIS license. And then you also need ArcHydro, which is a free add-on to ArcGIS, and it's a common tool that's used for watershed delineation. So we did take these different approaches for urban and rural areas, with the focus in the rural areas being on gully erosion from agricultural fields. And then in urban areas, we're taking this event mean concentration approach, looking at land use contributions to stormwater runoff. But you don't have to strictly think of these as urban versus rural tools. The urban or the event mean concentration tool could be used as kind of an initial screening step, where it'll identify, based on the land use, which are the areas that are likely to be contributing the most sediment or phosphorus, or any other parameter for that matter that you have the data for. And then once you've at a high level identified where those areas are. You could use what we're calling the rural tool to drill down a little more into those areas, look more closely, and see if there's gully erosion occurring, if there's the potential for gully erosion to be occurring. So I'll start by explaining the process behind the urban or event mean concentration tool. This one. So this is what the user interface looks like. And these are all the inputs that are required. So you have average annual precipitation in millimeters, your land use layer that has to have fields for event mean concentration, for your parameters of interest, and then percent imperviousness. You have your catchments, which will be basically the scale at which you want the results to be reported. And then you just have to specify the location of the output file. And I'm going to go through each of these inputs individually and talk about some potential data sources that you could use. So average annual precipitation, exactly what it sounds like, probably the simplest one and easiest one to find. You can get it from conservation authorities. Environment Canada is probably the best source. For example, the Pearson Airport station near us, and all the other stations will have the 30-year normals available, showing what the average annual precipitation was over the past 30 years, which is your best estimate, really, of what it might be in your area. So at Pearson Airport, for example, the one nearest to us, that value is 806.8 millimeters. And you could use future projections if you wanted to do that kind of comparison as well. But in this area, you're looking at values of around 700 to 900 millimeters. And when we ran it, I'll be using the Black Creek subwatershed, which is what you can see on the posters at the back of the room. So when we ran it on that subwatershed, we just use an amalgamation of rain gauges that are located within and around that subwatershed. But using Environment Canada is a great place to start. Land use data is also available from conservation authorities, for example, some provincial sources as well. So you'll need to provide a land use file that has event mean concentration as well. CBC has the ecological land classification data, so that's what we used. It has very detailed and specific land use classes. So we amalgamated some of those to get appropriate EMC concentrations for that. There's a few sources available for EMC data. For example, NSQD, National Stormwater Quality Database, is an American source that has event mean concentrations for lots of different land uses. There's locally the Sustainable Technologies Evaluation Program that has a lot of resources, including studies that have been done locally, where you can get more information. And of course, if you have your own data available, go ahead and use that. You also need percent imperviousness, which can be a little bit trickier to find. At CVC, we're lucky that we have a shapefile with our impervious footprint across the watershed. So we were able to use that to get estimates of impervious cover for all of our different land uses. So we will provide, along with the tool, all the values that we use related to our different ecological land classification classes. So if that's helpful for the end user to use those values and approximate them for whatever land uses they're dealing with, you can do that as well. So for anyone who isn't familiar, the event mean concentration is essentially an average concentration of a pollutant in stormwater during a rain event. And they're calculated by collecting water samples from a catch basin, for example, or some watercourse downstream of the particular land use that you're interested in monitoring. And you will set up a auto sampler that can collect runoff during rain events, where it will automatically fill bottles at a specific interval, depending on how long the event is expected to last, every 2 hours, 4 hours, 6 hours, etc. And then all of those water samples are combined together and weighted by what the flow was at the time that the sample was collected. So you can see in the picture here, these bottles on the top right were probably collected during the highest flows because they appear to have the highest sediment concentration. So those bottles would contribute a larger volume of water to the overall sample than some of the ones that were taken at the beginning and end of the event. So then once you have that composite sample, you can send that off to a lab to be analyzed for your parameters of interest. And then that process is then repeated for as many different examples of that land use as you can find, as many different events as you're able to, and averaged over time. So you end up with a representative concentration of what the flow events from that land use typically produce. Obviously, that's quite an intensive, expensive, time-consuming process, which is why we have these databases like NSQD that will amalgamate all these sources into one place so everyone doesn't have to go out and collect all this data each time. Yeah. So with all that information, this is the basic formula that we use to estimate our loading from our different land uses. This tool uses the simple method to estimate annual runoff. So essentially you're looking at what the annual precipitation is that was provided at the beginning and estimating based on imperviousness, how much of that is likely to actually run off the surface versus infiltrate and stay behind. So when you have that information, you can combine that with the area of the land that you're looking at and that event mean concentration to estimate what the actual loading will be on an annual basis coming off of that parcel of land. So that's what this formula is doing here. And finally, you need a catchment file as another one of your required inputs. And this can be any kind of polygon file. All it does is provide the scale at which the results are going to be reported. In our case, we ended up using quite a fine scale, like you can see here, relative to the underlying imagery. And this is just a snapshot of the catchments that we use in the posters at the back as well in Black Creek. But the scale that you're using is entirely up to the user. I mentioned that we did include an ArcHydro toolbox in the package that we're providing, and that tool can be used to generate these catchments and generate some of the other inputs that are required for the rural tool. So essentially what that will do is it takes a hydro and forest digital elevation model, and I will explain what that means when we start talking about the rural side of things. And it generates all the flow paths and delineates these catchments that you can see on the slide at whatever scale that you set. You will set a flow accumulation threshold, which is going to determine at what point a catchment will get delineated. That can be a bit of a trial and error process. Andrew will walk you through that later on, I believe. But that's a tool that can be used to generate these catchments. And then they can then be used as an input both to this urban tool and to the rural tool. Or if you don't want to use something like this, you can really use any kind of polygon shapefile, whether it's representing a neighborhood or a sewer shed or like a grid, if you wanted to do it that way. It's just a way of defining the scale at which you want the results to be reported. So this is giving you an example that you can also see on the poster at the back of what the results will look like. This is for Black Creek subwatershed, and it's color-coded by the different TSS loads, so total suspended solid loads that we estimated from these polygons. So this can be used then to prioritize areas that you may want to do some kind of management action in or investigate further. And just to note that we also adapted this methodology for use in our risk and return on investment tool. In this case, we used it to estimate the time until stormwater ponds would fill and require maintenance, but it's just one way that we have implemented this methodology elsewhere. And with that, I think I will pass it over to Andrew to walk us through a demo of how the tool works.
Great. Thank you, Lorna. I'm just going to take a second to get set up here. I'm going to open up ArcMap. Oops. Hopefully. Okay. Yeah, so thank you. Hello, everyone. Thanks again for joining us this morning. As mentioned, my name is Andrew Bilchak. I'm a specialist on the information management team here at CVC, and I've been here since 2022. I'm going to briefly walk through the process of adding the HITS toolbox into ArcMap, provide some background on the tool, and then I'll discuss the urban portion of the HITS toolbox. All right, so to get started, you want to open up a blank or a new ArcMap document. And yeah, just some background. So the HITS tool was created using Esri's ArcGIS program, specifically the ArcGIS model builder. Some of the rationale behind that is Model Builder is a low-code, no-code visual programming language built on Python. So it allows you to build complex geoprocessing workflows and does so by stringing together individual geoprocessing tools where the output of one process can be used as an input for the next process. So this was great for us because Lorna and Amanjot had already developed the methodology, as I said, in 2018, and we were just simply adapting it into something that could be automated and run over and over again. Our goal was taking that existing workflow and just running it with minimal manual intervention needed. Lorna mentioned that we modified it a bit. So previously, they'd been manually identifying where high SPI lines meet existing streams, for example, and that's something we tried to automate so that there's minimal manual work needed. We also had a tight timeline to work with developing the tool, so using Model Builder allowed us to have something that's flexible and easy to use and gave us more confidence that we'd meet the deadline on time with something that's fully functional. There are, of course, other options for running this type of tool. I'll talk a bit more about that at the end. There's open source geoprocessing tools that are great. ArcGIS Pro, of course, is becoming more and more popular. So, but for now, a lot of CVC still uses ArcMap, so that's what we went with. And I'll talk more about those other options towards the end. So as we mentioned, the HITS toolbox comes in packaged in something called an Arc toolbox, and it contains 3 tools. So the first is called the Simplified Basic Dendritic Terrain Processing Tool, which is a mouthful, but it's just a fancy way of saying that it delineates catchments for you. The second, or 2A, is the HITS Rural tool. And the third, or what we call 2B, is the HITS Urban or Annual Load tool, or EMC tool, which Lorna was just describing the methodology for. So for those of you who are familiar with GIS, just bear with me as I explain some basic concepts that not everyone might be familiar with. So this is ArcMap, as you can see. And once you've downloaded the Arc or the HITS toolbox, you're able to add it into ArcMap. You can do so by hitting this Arc toolbox button up at the top. And that opens up this sidebar here. So ArcMap comes loaded with all of these toolboxes by default, and we're using some of the existing tools in here in our model builder to create the HITS tool. To add the HITS toolbox, you would right-click Add Toolbox at the top here, and then you'd navigate to wherever you save your toolbox, highlight it, and hit Open, and then that would be added to ArcMap for this project. Once it's added, you can expand it here and then see the 3 tools that I mentioned. So the first, which we'll talk more about later, which is a modified ArcHydro model. Second, HITS Rural, and the third, HITS Urban or HITS Annual Load. So if you double click on any of the models, you're able to open them and you'll be greeted with this dialog box. By default on the right here, you'll see a short description of the tool and what it does. And then as you click through each parameter, the help on the side here will update with just a little blurb about what that parameter is and some helpful information like units of measurement. You can hide the help if you don't need it, or you can hit tool help to see the full list of help metadata at once. So as Lorna mentioned, the urban tool requires the following input layers: a land use layer and a catchment layer. You can add a layer in a number of ways. The first is by adding it to your map. So you can see I have a number of layers already loaded here in ArcMap. The second is, once it's loaded in the map, you can then drag it right into the tool. So you could put it in there. The second is to hit this little folder icon near one of the inputs, and that'll open up the Windows Explorer, and then you can navigate to your data and then select it and add. And yeah, so it's got two input parameters, or input layers rather, with these drop downs here. And then the rest are all parameters. So these are the fields that Lorna mentioned. Once you add a land use layer or catchments layer, you'll be able to select the appropriate fields from within those layers. They'll automatically populate in this drop down here. Annual precipitation is just an integer here, so you can modify that to 800, for example. And then once you have all your layers loaded, you can specify the output. It'll default to your default ArcGIS geodatabase, which can be managed in your environments here. And you can also navigate using the folder icon again. So the inputs for land use are the land use code, which is a text description of features that can be used to aggregate them. For example, in our CBC ecological land classification data, we have an ELC code, which is a shorthand for the land use. And then we also have a type field, which is just a text description, for example, intensive agriculture. And either of these could be used as the land use code. It just has to be something that you can use to aggregate all the features together. The second required field is the event mean concentration, which should be a field within the land use code. And of course, each land use would have the same EMC value. Each land use type would have the same EMC value. And the final required field is the imperviousness field, which is a impervious percentage for each of your land uses. The catchments layer must only include one field. We've named it Hydro ID here because that's the default from Arc Hydro, but it's really any unique field that can be used to categorize your catchments or your polygon layer that you're using to display the results. So it could even be just the object ID, which is a default. And yeah, once you have those loaded, you just run the tool. I'm not going to run it now because it takes a bit of time, but you'll be once it runs, you'll be greeted with results that automatically add to the map here. So for example, we have sub 10 total phosphorus, and if I zoom there, you can see that it's classified nicely for us. It's broken up into 5 groups using natural breaks. And it's a good idea to just double check that the data is classified correctly. So once it's added, you can right click on the table of contents here, hit properties. And if you navigate up to the symbology tab at the top here, it will already be symbolized in natural breaks. And you can just hit the value to double check that the ranges are correct based on your data. So the only field that's written for the urban tool is this sum load field. So if you open up the attribute table here, you can see that hydro ID, it's grabbing from the catchment field there. So this is just a unique polygon, and then some load, in this case for TSS, so total suspended solids. This is the full list of values here, and that's what's being categorized on the map. If you do have any null values in your data, you might get null results. So this is an example here, and that would just show up as a hole or a blank space in the data. So in that case, you could go back to your input data and make sure you don't have any null values. And I think that's it for the urban tool for now. Was there anything else you wanted to highlight? Running it? Yeah. Yeah, I'm just going to pull up a quick video showing the tool running. Yeah. And we'll make all these videos available as part of a how-to package along with a user guide. So there we go. So just going to walk through actually filling in the parameters here. Yeah, so once you hit OK, you'll see this new dialog box, which is just walking through the steps and gives you some information on what's actually being run in the background. And it's got a little progress bar at the top. The urban tool is the fastest of the tools. Depending on your area, for sub 10, for example, I think it takes about 2 or 3 minutes to run, so it's pretty fast. And if you have more smaller polygons or smaller catchments, it might take a bit longer to process. This video is sped up, so it wasn't quite that fast, but these would be the results, as I mentioned. And they're automatically added to the map. All right. I think I'll head up, pass it back to Aman for some words before a break.
So this was the demo of the first tool, which is based off event mean concentration. And like Lorna and Andrew mentioned, that yeah, it is more useful for urban areas where you have different urban categories, and depending upon like means how much data which you have, but it's applicable to any land use. If you have EMC for row crops, if you have EMC for grasslands, you can put it there and it will give you an overall picture at whatever scale. You can do it for a sub watershed, you can do it for full watershed, but you can even squeeze it down to say a sewer shed, right? So sewer network, and it will tell you that okay, I mean, if this is your sewer shed, then this is where the hotspots could be where you would like to focus on, and this is very useful if you or if somebody wants to implement say low impact development techniques, and it will tell you okay, I mean, these are the major areas where if you implement, then it will reduce. And what you can do is like means EMC, just an example here. For stormwater, water quality stormwater management pond, they're designed to reduce TSS by 80%, right? So if you have a sewer shed and you know that this much loading is coming, and then you can say, okay, if we design this a stormwater management pond, which will detain, not even retain, right? So detain 80% of the sediments, then you can put that efficiency in your EMCs, and it will spit out that by how much kilograms or tons of sediments or phosphorus will be reduced because of that effort. All the low impact development techniques, they have like the removal efficiency which you can use. That's where this tool becomes more handy, that it will give you the existing condition, and it will also give you future condition if you are deciding to implement certain type of practices in the area of your concern, right? So that's where the advantage of having this tool is as a screening tool at a bigger picture, but you can even zoom it down to a municipality or a part of municipality where you can decide that what type of practice will be applicable to that area, and what type of benefits you will be getting from implementation of these things. And this is always useful, even if you are doing like cost benefit analysis, that will tell you, okay, this much is what you will be spending, this much benefit you will be getting, and that's it. So cost benefit is not included in the tool, but that will something which you can use to, post process using whatever existing tools are available. There are tons of tools available on STEP website. Lorna mentioned about that, the sustainability technology evaluation program, which is basically the TRCA, CBC, and Lake Simcoe co-run that program, and whatever data we collect wherever goes there, so that it can be used as a local data, right? So that's a useful part of having that, and it also gives like if you want to have your own local data, then it will tell you that how you should be collecting the data and using for further evaluation. So that was the main philosophy behind developing this tool. Like I mentioned, that if IJC wants us to reduce or maintain 10 milligram per 10 microgram per liter of total phosphorus concentration, right? So that's where you will see, or if whatever it was, 7,000 metric tons per year, then if you evaluate from your modeling or other exercises, or even applying this tool, that this much is coming out of your main watershed, then you say, okay, you implement these type of techniques. There's where you will get the best bang for the buck, and implement those, and that's how it will reduce. So it's a very handy tool. It's relatively simple. Most of the information, like in Ontario ecological classification, data is almost available with every conservation authority. You can have that layer. It's also available through MNRF, and also soil data, which we'll be talking about later on, is also available at a number of sources, but I won't talk about that at this moment. I'll let Lorna speak about that after our break. But I'll open the floor for any questions. I'll give those who are in person here first chance to ask the questions, and then I'll open the floor for those who are online, and then we can start answering those questions. And Jessica, you will help me with that, right? When the online thing is Sakshi. Sorry.
Okay, I wanted to ask for the input files if we have a template or the asset ID name. Is that on the help? Like, I think you open the help where you have the, like for the input files for the tool.
Yep.
Yeah, just to make sure we're putting it in the right template and the tool doesn't reject them then.
So that's the beauty of this tool, that it doesn't have to be on a particular column. You can change the name of the column. You will just tell it when you are populating that this file, this column should be used for this one, right? So again, you have, am I right? Andrew, I'm speaking for you, sorry.
No, you're exactly right. The help does mention like what format they have to be in, data format, but otherwise, yeah, you can just select the appropriate field.
Any other, yeah, go ahead, Sakshi. Yeah.
Okay, my second question was for the, like, I mean, you were just mentioning that you have like this goal of 7,000 metric tons for Lake Ontario. Have you thought about generating like another sort of target per watershed or per municipality so we know what to, like, from our jurisdiction, what our target should be for TP?
Not at the moment, but we'll be getting there because once we'll start, working on this tool or our, Mike Shee models, we'll understand better that, how much is coming from different municipalities, and we'll like to work with our municipalities that how, we can reduce those loadings, right? And yeah, go from there. Yeah. But good point. Yeah. Any other question? This is targeted for two things: agricultural areas for sure, is to look at the how the farms develop those type of gully erosion. So we are not talking about real erosion. We are just specifically talking about gully erosion and where the potential of getting those gullies would be in the farm, and those are the main sources where ultimately we transporting extra water and also channeling the sediments and sediment-bound contaminants. So I, and at the end, I will also show you that because it's not just developing the tool or thing. I'm so happy that our agricultural outreach folks, they are using this maps produced from this tool as an outreach activity, talking to the farmers and explaining to them that where they may see current gullies and where they may see gullies in future, and what type of practices would help them not to lose. The more important thing for farmers to know is that they should not lose their soil, because that topsoil is rich in nutrients. So it's not only just contaminating our receiving waters, but it's also hurting them by not utilizing those sources, those nutrients which are already there in the soil and could be easily used by the crops and preserved there, right? So I'm so happy that it's been used, and also it will be used in future for other natural remedies, so that these type of prevention or preferential surface flows don't happen through the gullies and other stuff. So I'll give the floor again to Lorna to talk about the second tool, and then Andrew will follow up on that, actually demonstrating the tool. Here you go, Lorna.
Give me a second to switch presentations. Okay, we're gonna have to click through to get back to the rural side of things here. Okay. All right, so I will go over some of the underlying concepts and provide an introduction to the rural tool. So we call it the rural tool, but it is designed to identify areas that are potentially vulnerable to gully erosion. And just to provide some background on the different types of erosion that you might find in agricultural areas, there's sheet erosion caused by sheet flow over a surface, often a sloped surface. Sometimes you wouldn't necessarily see this type of erosion with the naked eye, but it could be happening. Secondly, there's rill erosion, which is what happens when that flow starts to concentrate a little bit more into small streamlets or rivulets, but it's still minor enough that it's something that could be corrected with tillage practices, for example. And then you get down to gully erosion, which are these deeper scours in the soil that will happen in low-lying areas. Even if there's not a major elevation difference across the field, you can still see these start to form in low-lying areas. And this is severe enough that it's not easily repaired with tillage. And if you see erosion like this happening, then it's very likely that there's a lot of sediment transport and nutrient transport that's happening along with that, removing nutrients from the soil and also contributing it to watercourses where we don't want it to be. So this type of gully erosion is really what we're focusing on with this tool. At a high level, this is what the methods are. We're looking at the catchment scale areas that are vulnerable to gully erosion, and then it further gives you the ability to zoom in on those catchments and see where those might actually form. And then, as Aman mentioned, those maps can be taken to present to landowners to show them exactly where they might have vulnerabilities occurring on their fields. So it starts with catchment delineation, the same as you would do for the urban side. And I will go into the details of that in the next few slides and explain how you would prepare a digital elevation model for this work. And then ultimately it uses stream power index, which is a function of flow accumulation and slope. And that is the part that really identifies where these gullies are likely to form. We've also combined it with soil erodibility, so that gives you that added layer of not just where the topography is telling you that erosion might happen, but overlaying it with the soils that are, by their nature, more vulnerable to erosion. So terrain pre-processing is a really important step in this tool because your terrain is what is determining where gullies are predicted to form. The top window that you can see on this slide is that ArcHydro tool that I mentioned is included with the package. It takes a filled digital elevation model and uses it to create catchments and a flow accumulation grid. And those two things are then key inputs into the tool itself. So this ArcHydro tool requires a hydro-enforced DEM. So that is a DEM where every single cell has a flow path to the outlet. So you don't have a metaphorical or digital water droplet won't get stuck in a particular area and form a pond. So there's several ways and tools available to create this hydro-enforced DEM. And if you look at the two figures that I have, the middle one is, imagine it's like a slice of a digital elevation model. Each of those bars is representing the elevation of that cell. And on the left, in here, you have a sink, essentially, where if a droplet of water were to land on that cell, it would be stuck and it wouldn't have anywhere to go. And the tool isn't going to work unless every single cell has a flow path downstream. So this is what we're trying to correct for, and there's different ways to do that. The simple way with built-in tools in ArcGIS is just to fill sinks. So what that does is it takes the elevation of that cell and just keeps artificially increasing it until it gets to the point where there is now a downstream flow path. And that's what you can see is happening here. It's just been filled to the point where now it's level with the next highest cell and it can start to flow downstream again. But that can have the side effect of creating artificially flat areas. And if you're dealing with a landscape that doesn't have a lot of variation to begin with, then that can really impact the flow paths across the landscape and where these predicted gullies might happen. So then there are more complex tools available, and this lower image here is an example of the optimized pit removal tool. This is another ArcGIS or tool that can be added onto ArcGIS, where it has a more complex methodology that includes not just filling sinks, but also what's called cutting cells away. So it's going to look at the digital elevation model and say, I could either, like in the first example, increase the elevation until there's a flow path, or it could cut down the elevation until there's a flow path, or do some kind of combination of both. So when you use a tool like this, you end up with fewer overall changes to the underlying model, which can give you a more accurate representation of flow paths and reduce the chances of getting these artificially flattened areas on the landscape. So we did not include this kind of terrain pre-processing in the model because the choices that the user might want to make could be really dependent on the specific area that they're dealing with and the specific tools that they have access to. So we didn't want to force either, on the one hand, force the user to use the really simplistic built-in ArcGIS tools, or have another required tool such as optimized pit removal. So we're providing these as suggestions for what you can do for the pre-processing, but then the tool that we have developed will require as an input a flow accumulation grid and the catchments. So your workflow would essentially be doing the terrain pre-processing, so whichever fill sinks method you want to choose, and then running this ArcHydro tool to create catchments and to create a flow accumulation grid. And at that point, you will jump into using the tool that we have created here, which requires the following inputs. And like I did with the urban one, I will go through each of the inputs one by one and talk about some potential data sources. So we have a digital elevation model, a flow accumulation grid, our catchments, a land use layer, some soil data, including a soil erodibility factor, and then you would need to specify the location of your output files. So we talked about the DEM in detail already. So you can use in this as an input to the tool your pre-processed hydro-corrected or hydro-enforced DEM. But at this point, it's really only being used to calculate slope. So if you wanted to use a different one, you could, but you might as well just use the same one that was used in pre-processing. And there are federal government and provincial government, like the Provincial GeoHub, sources for high resolution DM data. I didn't talk about the resolution previously. We've been using 1 meter resolution DEMs. Obviously, it'll depend on the scale of the study area you're looking at. We found 1 meter was sufficient, but the finer resolution you get, the more likely you are to be able to specifically identify gullies if you're able to do the terrain pre-processing correctly. You also need a flow accumulation grid. So this is a grid that would have been created during that pre-processing step using the ArcHydro tool that we're including in the package. And this is probably the most important of the input files because this is showing you where water is starting to accumulate on the landscape, and it'll eventually start to form a watercourse if you follow this far enough downstream. But what we're looking at in terms of gullies is essentially where water is beginning to accumulate, but not to the point where a full watercourse has been created yet. So these have to be generated from a DEM. I'm not aware of any alternate sources of this data, especially at a 1 meter resolution. But as I said, we'll provide guidance on creating this. And you might recognize this slide from the previous presentation because the catchment inputs are the same or can be the same as the ones that we used in the urban tool. So once again, it can be any kind of polygon file. It doesn't have to be catchments, but it makes a lot of sense to use those because the stream power index is really driven by that topography, by these kind of catchment delineations as well. So using the catchments is a great idea here. And they will be generated by that ArcHydro tool as well. So land use is technically a required input for this tool. It can be based on the same land use data used in the urban side of things. It doesn't require any of the extra fields like event mean concentration or imperviousness here. In our case, we were specifically interested in erosion on agricultural fields. So what we did is we just extracted all of the agricultural land uses from that land use file and plug them in here. So you can see on this slide, it's just pulling out those agricultural areas, and we're not looking at anything else. So what this input file will do is limit the analysis to those specific areas of interest only. So since we're looking at gully erosion from our perspective, if there was a gully forming, in the middle of a forest somewhere, we weren't that interested in it because with all the vegetation, it's unlikely that you'd actually see a gully forming there, and it's unlikely that there would be a huge amount of sediment or nutrient transport happening as well. So we limited it to agricultural areas. With that being said, it can be any polygon input file. This is how we chose to do it. But if you just want to look at rural land uses in general, or if there are any other types of land uses that you are interested in terms of gully erosion, then you can include that. Or if you want to include the entire study area, you could just include a single polygon that encompasses the entire study area, or use your same catchments polygon as well, and then it will just it won't be limited to agriculture. It'll just run the tool for the entire area. We have soil data as well available from the province. They are quite coarse in terms of the spatial distribution. And there's a screenshot here of the government website where you can download all this data. You'll see some quite old dates on there indicating that this is long overdue for an update. But that being said, it does exist for the majority of the province, which will give you that spatial distribution of soil data. And then once you have those soil classes, you can dig down really deeply into the attributes of that soil. And you can get all that information on the link that I have posted here, which gives you the table at the bottom of the slide, which has all the information you need to calculate erodibility, like your soil texture, your percent sand, silt, clay, organic material, etc. So when it comes to calculating erodibility, we used this formula, which comes from the original universal soil loss equation developed in 1987. It uses particle size, which is calculated from all the different soil texture parameters that are available online that I showed in the previous slide. So you have your particle size, your sand, silt, clay, that's all available if you look up your soil type on that website. And the soil structure class and soil permeability classes are available through a lookup table in that original 1987 document that I've referenced here. So the tool doesn't do this calculation itself. This is just to show you where we developed our own erodibility factors when we run it ourselves. But we'll provide this information for you for the users to calculate. It also, we wanted to give the user the ability to use the best data available to them and, not dictate the K factors that they have to use in the calculation. So whatever sources the user has available, use those. And it'll be similar to the previous tool we looked at where you select your land use and then there'll be a drop-down menu where you select the field that contains your K values. So finally, stream power index is calculated, and the formula for that is the natural log of slope times flow accumulation. So the slope is calculated in the tool as in percent rise, and then the flow accumulation is simply the number of cells that drain to each one of those cells on your flow accumulation grid. And this calculation is done inside the tool. So the way we're using it by looking at stream power on land, it's measuring the power that water moving over the land has to erode the soil underneath it. So if you have a higher slope, for example, your water is going to be moving faster, and that's going to have a higher power to erode the land. Similarly, if you have a higher flow accumulation, then you've got a larger water volume, and that's going to have more power to erode. So that's why the stream power is driven by these two factors. And what you're looking at here is stream power over a section of our study area. So you can see that every grid cell, almost every grid cell, is given a stream power value. There are some gaps where I believe that's because the slope is 0, so it isn't able to calculate anything. But the entire study area is given a stream power index. So we needed to narrow that down and figure out which ones of these actually represent areas where gullies can be formed. So through a little bit of trial and error, we ended up selecting the 97th percentile. So if you take all of the stream power values that are in the 97th percentile and up, you get something that looks more like this, which is looking more like a mini stream work in essence, and where you see those red lines, that's where you're getting to the 99th percentile, and that's where you might start to really see some gullies forming. So this 97th percentile threshold is hard-coded into the tool, but it is open and available for everyone to look into on the back end, and if you have experience with Model Builder, you can go in there and change that yourself if that percentile isn't working for you. And then the final step is to bring it all together. So for each of the catchments that we input at the beginning, there's going to be 3 things that are calculated. There's the area weighted K factor. So we're taking that catchment and looking at each soil type within it, and then just area weighting the erodibility of that soil so that you get a representative value for the catchment. And we're doing a similar thing for the stream power. So all those stream powers then get converted into lines, and they're weighted based on the percentile. So stream power lines that are in the 99th percentile are given a higher weight than the ones that are in the 97th, for example. And then that weight is multiplied by the length of the line. And then those values all get summed together and applied to the catchment as a whole. So you get a weighted stream power index length for that catchment. So those numbers, the area weighted K factor and the weighted stream power index length, aren't very intuitive or very useful by themselves. So we normalize the values to a scale between 0 and 1. So that way, these two values, which yield very different numbers, are actually more comparable to one another, and they provide a more useful scale for ranking vulnerability. And ultimately, we then just average those values together to get something that's representative of the combined vulnerability to both gully erosion and soil erosion. So you can then produce an output that has all the catchments displayed, and you'll see that on the poster on the left. You can display the catchments ranked by vulnerabilities just to stream power, by vulnerability to soil erosion, or by that combined vulnerability. And once you've identified the highly vulnerable catchments, then you can zoom in, and those stream power lines will be available, so you can actually see on an individual field where a gully is potentially forming. And a lot of the time, if you put, and you'll see on this poster as well, if you put the aerial imagery underneath, you'll see kind of scarring on the landscape that's happening exactly where this tool is predicting that the gullies might form. Okay. With that, I think I will pass it over to Andrew again for a demo of this tool.
All right, thanks, Lorna. Just gonna pull up ArcMap again. Okay. All right, perfect. So as we mentioned earlier, after you add the HITS toolbox to ArcMap, you have the 3 tools. We've already gone over the annual load or urban tool. So now we'll talk about the first 2 tools. The simplified basic dendritic terrain processing tool is the one that we've modified from ArcHydro. ArcHydro has something called just the basic dendritic terrain processing model, and it includes a bunch of outputs that aren't relevant for our needs. So we've just removed those and simplified it to streamline the user's experience. It does require the ArcHydro extension, which, as Lorna mentioned, is a free extension that's available through Esri, which makes ArcMap. And it's just like a file that you install on your computer, and it adds a bunch of toolboxes that you can see up here as well. So running the simplified basic dendritic terrain processing tool is similar to the other one. You double click it to open it, and you'll be presented with a dialog box with only one input, which is a filled DEM. So you can see, again, you have the help on the side here. As Lorna mentioned, the more pre-processing you do on your DEM, the better. As they say in GIS and most data analysis circles, garbage in equals garbage out. So definitely this is a step that you'd want to pay a bit more attention to. There are a number of ways to prepare your DEM. There's just simple filling, like Lorna mentioned. Stream burning is another one. If you have a stream network available, you can burn those streams directly into your DEM to break those digital dams and prevent any of that artificial water buildup. At CVC, we've undergone some manual hydro enforcement, so that involved zooming in on areas, on even culverts, and just like manually cutting those areas so that the water flows properly over the surface. Obviously, you want to remove big things like pedestrian bridges or car bridges, but a lot of times LiDAR will already remove those for you. So once you have your DEM, you would then fill it, and you would select it here as an input to the tool. And then this parameter here is the number of cells to define the stream, or what's called the stream threshold. And as Lorna mentioned, it defines how many flow accumulation cells equal to a stream. So basically, this tool is creating 2 rasters or grids. One is a flow direction tool, and for every grid, it's assigned a value of which direction the water would flow. So it's usually 8 directions, so left, right, up, down, and then diagonally. There's also, I think, a 16 and 32 direction flow direction grids, but we're using the 8-bit flow direction. And then after that, you get the flow accumulation. So the direction those cells are flowing, once enough cells flow into one cell and hit this threshold, that would then define a stream. By default, it's just set to 5,000. That's just the ArcHydro default. If you run the tool separately outside of this model in ArcHydro, they recommend 1% of your total area of your DEM as a threshold. So if you have a 1 meter DEM, you can just calculate how large your area is and then get 1% of that. We found around 1 to 5% gave us good results. The The smaller your threshold, the fewer cells you need to define a stream, and therefore your catchments will be generally smaller because you'll have a whole bunch of these tiny little streams everywhere. If you use a number too large, then you might just get one stream, and then you'll have a gigantic catchment that would not be useful for your analysis. So if you find the results aren't meeting your needs, you can come back here and modify the threshold. So then, yeah, once you have these parameters, you click OK, and I have a video as well just showing that quickly. So here we have our filled DEM, which is the only required input. And then selecting it. And the threshold, modifying it, it's just an integer value, so no decimal places. And then you hit OK to run it. Right now we're running it on a sub catchment. This is sub catchment 1610 in CVC, so not a very large area. I think it takes just a couple of minutes to run. As the tool runs, it spits out a couple of outputs. So it'll give you that flow direction raster, the flow accumulation raster, a catchment raster, and then finally your catchment polygon file, which will be your input for tool 2A and 2B. So there's the flow direction. You can see the numbers. So it's got 8 numbers. So that corresponds to which direction the water is flowing out of the cell. Speed along here a little bit. The flow accumulation stream raster. And this is your catchment raster behind there. And finally, you get the catchment polygon. So these polygon shapes are really the only output you need from this tool, but the other ones let you explore your catchment a little bit and make sure things look correct, especially the stream and stream link rasters. Those show where streams are generated, so those are useful to explore. Just going to switch back over to ArcMap. Okay, and then yeah, now I'll talk about the rural tool a little bit. So the rural tool generates catchments that contain a stream power index rank and erodibility or K factor rank, and a final combined rank based off the other average ranks, or based off the average of the other ranks, as Lorna mentioned. So these are the input parameters. We'll just go over them again quickly. The filled DEM, which you can use the same one that you used for the first tool. The flow accumulation raster, which is used to calculate your stream power index. The catchments polygon layer, and then your land use or area of interest. So for us, we use the intensive agriculture areas from CVC's ecological land use. But this could be any kind of polygon where you want essentially the high SPI lines to be clipped to be intersected with. So you can see where there might be gully erosion forming on those polygons. This will also intersect the soil layer with those areas of interest, which should contain a K factor field. So once you load the soil layer here, you can then select the corresponding K factor field from your soil layer. And the tool will spit out two final outputs. The first is those catchments with the 3 rankings. So I'll show those in a second. And the second one is just your top 3 percentile SPI lines, 97 percentile and up SPI polylines, which you can overlay over your catchments to do some more exploration and see where specifically those gullies might be forming. So if I turn on one of our examples here, we can see right now I am symbolizing this catchment by the final combined rank. So that's the average of the K factor rank and the SPI rank, both of which have been normalized. We just open up the attribute table here. We can see it's been given those ranks here towards the end. So SPI rank is the SPI polyline weighted ranking for the area, for the catchment. So each one of these records corresponds to catchment. And then the K rank is the erodibility or, the K or erodibility rank. And the final rank is the average of these two normalized rankings. If you wanted to symbolize one of those fields, you would just go to the properties and you can change what you want to see. You can also duplicate these, so you can just copy and paste them and then symbolize by a different field so that you can compare them more easily by just turning one off and on. And then if we look at the high SPI polylines overlaid, and it's just thinking while I try to zoom in. There we go. Okay, so you can see this. This catchment has been given a low ranking, and you can see that the SPI lines, while it does have a 99 percentile SPI line, it doesn't have too many SPI lines in total in this area, so it has been given a low ranking. Something like this, you've got some more SPI lines. They're longer, so that'll be given a higher ranking. If you go something like this is one of the highest ranked SPI catchments, and you can see we've got quite a lot of SPI lines, and the area of the catchment is also pretty well covered almost entirely by SPI lines. So that's why I get such a high ranking there. Okay, so yeah, after the tool runs, the outputs are added to the map, and then you can do all this exploration. Again, it's pretty quick. The rural tool is the most intensive of all three, so it does take a bit longer, but for our subcatchment study area here, took about 10 minutes to run in total, so still not too intensive. The most intensive process is the slope and SPI generation. A lot of the other stuff is just the calculations that Lorna had mentioned and joining that data to the correct layer. So next steps. So I mentioned at the start of the presentation some of the reasons why we chose to use Model Builder and ArcGIS and ArcMap for this tool. In the near term, we'd at least like to transfer the tool to ArcGIS Pro. It is backwards compatible with ArcMap, and all of these tools are just built in Python, so it's a pretty straightforward process to bring them over to ArcGIS Pro and just test things out quickly. A lot of organizations obviously are already transferring to ArcGIS Pro because ArcMap is nearing its end of life very quickly. So that would make the toolbox more accessible and allow more users to use it in the future. However, even then, users would still need a paid GIS to access the toolbox. So if we do have the funding to do so, we'd love to recreate the toolbox entirely in Python using standalone free and open source geospatial tools. We've already started some research and exploration into some of the options out there. There are some great open source libraries like PySheds for catchment delineation and some water resource management. So that is our dream. That's the next step. And obviously a standalone tool, if you don't need Esri, a subscription to ArcMap or ArcGIS Pro, then that really opens up the accessibility and flexibility because there's really little to no cost entry. Next, I think Aman's going to show some drone fun stuff.
Well, thanks, Lorna and Andrew. Big applause for them. They did an amazing job here. Well, it's not only like, creating a tool, but timely creating it within the time limits and within the budget was the main thing. And they did an amazing job. I've tried many times with my team to work hard, but they are so smart that they still would have time to think whether S should come before it or after it. And that's what makes my day, right? So I'm so happy and so proud of them, and that they make me so proud standing here and presenting on these things. Thank you so much, folks. You're great. So I mentioned that we intend to use some other cutting edge technology also to verify what we are doing is in the right direction, and also the outreach activities, so that the work which we are doing here, which demonstrates that where to go and how to communicate with farmers and other landowners and implement the management practices which are already available through different sources. So I'll talk a little bit about that. What's it? Oh, yes. Sorry. Yeah. Any questions for Lorna or for Andrew on the rural tool? Again, open to the who are here attending in person. If not, then I'll open it for online. There's none, right? Okay, so I'll move on. So there are always two things, right? Either everything is going overhead, or everything we are so clear in our thoughts that you're understanding everything. You have no questions at all. Perfect. Either way, I'm happy, right? So okay, I'll bring my presentation here. Okay, so we'll move on, and we'll move to the slide where we'll talk about the other stuff right now. So again, like I said, that when we first developed, we wanted it to be used as an outreach activity, and at that time, our agricultural outreach person, Mark Eastman, was here, and he used to take these maps which we have created to the farmers and talk to them over. And now I'm glad that Holly is here with her team, and they will be, using these tools. What we need to train them is, for whatever level they want to, run this tool, they will be independent. They will be able to independently run the tool, create these SPIs, and talk to the farmers to do the outreach activity and see what the buy-in is. But in the first round, what we did, it was very successful. Farmers are open to see that where their fields are prone for erosion and soil removal, and they were trying to explore what management practices should be adopted. So this is one example of one of the farms where we did the SPI, and then outreach folks went there to talk to the farmer. So this is a farm field in one of the sub-watersheds, and this was the SPI just created for that farm, right? So, and you see here where the red ones are, where it is showing that, okay, I mean, these are the areas which are more prone to gully erosion, but it's starting up front, so you have to, adjust according to your field layout and then see that how, those can be managed in a better way so that, the soil erosion doesn't happen. And this is actually we went to the field for field validation, and this was one of the things where you see this this particular area, this area where the gully was already forming, right? So if it has formed already there, that means you need to adjust this entire area and see what management practices need to be done there so that this stuff doesn't happen or actually reduces the erosion. So those are the initiatives which are very important, and if they're visual, you're showing them on the farm scale. That's where the actual value lies in, right? That you're demonstrating. It's not on the paper only, but you're going out and using these tools to tell what advantage they will have if they start adopting to the management practices which OMF, say for example, for agricultural areas they already have it, but again for other methods also they can adopt. So this is the stuff which again through this this is CWA funding again. We wanted to introduce. We bought some additional sensors, the LiDAR sensor and the multispectral sensor, and we wanted to see to one of our newer sites where we applied the tool and see that, okay, how does it translate with a very high resolution LiDAR data, and I'm talking about 20 centimeter by 20 centimeter, right? So that is what the resolution, if you are applying it for a very small catchment, that's the kind of resolution which gives you even more details on a smaller scale. So unfortunately, I'm jealous that I could not go that day. I was sick, but but I'm proud that the team handled it very well. And the vendor was also there from whom we purchased all the equipment. They all went, and some of them who already have the drone flying licenses, they did fly the drone there and did practice, and I'll show you what they were doing when I was not there. That's why I call them as smart guys. So you see, this is the drone which we flew, and rather than just flying it straight, they did some dancing to the actually this was the important piece. I'm just kidding, because this is how you learn to control a drone, and that was important, right? So it's but again, learning something with fun is always which is really great to do. So this exercise went very well, though we were a little bit skeptical because this time winter was long, and the snow, patches of snow was still there, but still the resolution which we got was really amazing. So again, this is the farm where we generated the new SPIs based off both the slope and accumulation and the soil erodibility. And this is how the SPI line, just integrated the network looked like. And when we post-processed the DEMs which we received from our drone run, you will see this is how it looked. So it's phenomenal information which you are getting from these type of tools with very high resolution data in that, right? So this is what we wanted, and you see that where the higher lines are, where the higher slopes are going from white to green, and that's where you will be informed that okay, means how the practices should be done, so that these type of streamlines are not getting worse with every storm event. And this is a one which is actually weighted, which tells you that the darker the color tells you that the SPI is really high, and the whiter ones are the SPIs are still, there are chances of higher gully erosion in these areas, but they are still under formation. So if the practice is like the common practice would be like you have some residuals on the land which prevent these type of preferential flows to happen when spring or rain in these areas happen when the crops are not there. So these are the things which are very essential, and if we really want to reduce the phosphorus transfer or the sediment transfer, or loss of soil from the field, we need to go to first identify at a bigger scale which are the catchments which are more prone to these type of activities, where there will be a better reduction available, and then when you go and talk to the actual landowners, then you can show that what type of practices will help them. So it's basically you're talking to them, showing all these things, make sure so that they relate it to their own field and they are willing to do that, rather than considering to enforce forcefully anything. This is kind of a walking with them and demonstrating. So additional results which we got from this, again, which are very helpful for scientific advancements, is it's not only taking the DEMs, but with the multispectral and other stuff, we are also, this is the RBG. So you see that there was lots of snow cover still there, but even then we got very high resolution data, and you see the patches here. And additional information which you get from is that you get the reflectance, right? So reflectance tells you is there a drainage issue in a farm, or which areas could be requiring some further attention based upon means reflectance of the area. The blue things which you are seeing on this, these are actually trees. And the red things which you are saying is like higher moisture content and all the stuff, right? So these are, again, if the drainage is improved and there is opportunity for water to infiltrate out the runoff, that's where the benefit lies for reducing erosion activities. And this is actually again coming up. You can measure the height of whatever vegetation may be there. Again, a very useful tool, especially if we are converting a land area back to wetlands, and how that wetland would progress is an important tool to again have in our back pocket, and see how this is in long run is going to help us understand about the land use, and also about how the restoration in helping in steps changing the landscape, so that the SPIs are reducing from higher number to lower number, and making the land uses resilient to any kind of erosion. So these are the main things which we wanted to do to accomplish in this project, and I'm glad we have the tools available, and we'll be sharing them. We'll be after our recordings are finalized and the package is ready, I would say by the end of April, we will be circulating where you can find the tools to download, or where the presentation will be uploaded. it will be probably coming as one package, so that if you want to use it for your stuff, you can take it from there. It will be open source. You can, if you some other conditions, depending upon, again, you have to be careful that none of these tools are cookie cut tools, right? You have to apply some understanding on, like, when you are applying, it will give you basic information as it is with all the numbers which we have used. But if you are in a different area under different climatic zones or the soil conditions, then you know better about your watershed, your sub-watershed, and how the properties may change. So you can tweak that, change the numbers and apply that. But again, it's a very promising tool, right on the field scale up to the sub-watershed scale, that you can prioritize your activities and see how much reduction can be done for that. And like I said, the previous tool, which was based on event mean concentration. So once you apply those kind of best practices, you can again then maybe based off like whatever retention or detention you are expecting, you can reduce the EMC numbers and see that what benefit you are getting because of that how much percent reduction you can expect from your sub-watershed and catchment. That's what will be, where the tool, both these tools will be helpful. And it also comes, like Andrew and Lorna mentioned, with the tools that you can create your own catchment and stuff, and that's where it used to be handy. I say, Holly, do you have a question? That's what I want to hear. Just to let everybody know, Holly is excited. So Holly is our agricultural outreach person, and this tool definitely is going to be transferred to her for use for wherever she wants to, right? So that will be fantastic. So again, thanks for you folks for providing the funding. It was excellent, and I'm hoping that you like the way the tools have been developed and the way we delivered our stuff. So the main thing where I always emphasize is that I only commit for that what can be delivered within that time, and I think we did. So I'm happy about that, and of course kudos to all the team members who really worked very smartly in developing the tool and getting it out to this. And again, it's not the science. Science makes sense only if it can be also used by others, and so we don't want to detain anything here. We want to expand that, and if anybody else who is listening to this talk and understand better, feel free to share your thoughts. We'll be happy to see that if this tool or something else can be done to modify it to make it actual a tool which can help us addressing our questions like reducing phosphorus or sediment or any other contaminant loading to our receiving water bodies. And as you know, the climate change is going to advance our other thing. Urbanization would be another thing that we may see some more challenges, and as we take the steps in the proper direction, I think we'll be able to achieve targets which are being laid out to preserve our Great Lakes and let them be great forever, right? All right. If there is any question, please shoot it now. Any? Yep, Sakshi.
Really excited as well, just like Holly, to see this presentation. I was wondering, at a municipal scale, if for a primarily urban municipality with a couple of farms, maybe 40, 50 farm properties, what scale of DEM do you think is suitable to do the rural SPI line?
Okay, so if you decide to hire us, then we'll use 27 meter, right? Sorry, jokes apart.
Yeah, I was wondering, like, if you had to do drone analysis for one property versus like 50 properties, does it get really expensive?
Well, the thing is, you can start with whatever is available, say 1 meter resolution if it is available. But if you really want to go to the finer resolution, then you will need to get a higher resolution. So 1 meter is an excellent start, right? So people have used 5 meters or 10 meters, right? So 1 meter is an excellent start. But honing on to like means actually specified focusing areas, then you will need to get below 1 meter. And yeah.
And you'll also be able to validate, like how good is aerial imagery to validate sort of your gully?
Well, again, it's all resolution specific, right? So satellite imagery is not going to give you 1 meter resolution, right? So 1 meter resolution is usually from by flowing the LiDAR on an aeroplane or whatever, right? So that gives you better resolution. I don't know means how quickly or what's available. Lorna has an answer.
Don't necessarily have an answer to that, but I just wanted to say when we were looking at the first time we ran it, there are some cases where you look at the aerial imagery and you don't see it, but it's because the farmer may have already implemented some kind of management practice there. So that's the kind of information that you don't get from an image. There was one case where they had a huge problem with gully erosion. They'd already implemented like a berm and tile drain to deal with it. So that kind of thing you can't tell from the imagery. Yeah, so sometimes you need that site-specific information.
Yeah, and we are seeing interest from other municipalities too, just to sell. I mean, it's not only for this SPI stuff, but the sensors which we have now can also help in other activities like how the stormwater management systems are working, especially with the new government policies that can we use these drones for the assessment of our infrastructure. Even I'm looking into getting another sensor, which is a pressure transducer to provide bathymetry of stormwater management ponds. So this current sensor can do up to 5 meters. We have not tried it, but that's what they claim. So if it is 5 meters, then we can do, even with this LiDAR, we can do stormwater management ponds because their maximum depth is 5 meters, right? So maybe we'll try that out in very near future. But again, there are sensors available where you can do actual bathymetry using the drone, which is much quicker, and we can assess. And also, the same flight will cover that how much vegetation is there around the pond or around the critical infrastructure that can be mapped and can be done more frequently. Yeah, so that's where additional advantages from the urban perspective for the urban municipalities which we are seeing. And on top of that, even this SPI has been also used for stream erosion stuff, right? Because but then the scale becomes different. We were more focused on the farm scale, but you can also do it for the river reaches and stuff and see where intersections have high SPI and where the correction may be needed. Again, with the LiDAR data captured from the drone, we can do pre and post any bigger storm event and see that how much erosion has happened, and with SP, I think what could be the next trigger level, right? So these are all coming together very nicely and very practical use of these things together, and it's cutting edge technology, right? So getting 20 centimeter by 20 centimeter resolution is just fantastic for especially these things. And we sometimes struggle for our hydrologic or our water quality models because when we are delineating the stream network, it doesn't come to that accuracy, right? Especially the low flow channels, which are very important. But with this type of technology, we'll be able to delineate our water courses much better, the cross sections, to feed into the model. Like Andrew said, garbage in, garbage out. So if we want actual good data in, we'll definitely get better answers from our models too, right? And that's what we are trying to do. Any other question from anyone? Danielle.
Awesome. Thank you so much for the presentation. I just had and the whole event. In terms of the scale at which you've applied the tool within the broader watershed. So with the examples that we showed today, the focus was on some of the sub-watershed scale assessment to kind of as a proof of concept in terms of how it's being applied. And so based, I think, on some of your questions as well, in terms of next steps, in terms of applying it to other parts of, the credit watershed as well, is that kind of what you're thinking?
So I will start with a joke. I'm waiting for some more funding. Sorry. Well, that's why Holly is excited about, right? So this tool, the way it's developed, it's pretty straightforward to use it, and we have internal resources to work on. We'll be doing some projects with Halton region and Halton Hill, town of Halton Hills. We will be using this tool. But again, wherever the focus comes in, and it doesn't take much time to apply this. And that was the reason we wanted to make it as a tool. So that means it's not that only the core group is using it, but it's usually user-friendly enough. It has a very good GUI, simple GUI, which will tell you what to bring in and run the model, and it doesn't take much time, right? So that's a big advantage of having this, right? So, and again, if somebody else somewhere else wants to use it, it's there, right? So you don't have to reinvent the wheel, but you can make it better if it suits your needs for certain other stuff, right? But this already is a solid base is already there, and you can take it from there.
I don't know if Holly wants to speak about it, but yeah, like we already have a project lined up, or hopefully lined up, to look at specific properties in subwatershed 10. So that's going to help us scale the model down. But
yeah, we actually have secured some funding to prioritize annual crop producers in subwaresheds 10 and 11. So we will be using the final ranking map right there. We'll be looking for all the cash crop farms in the red and working really closely with them to provide them with lots of really great tools to help them manage their soil really well and prevent erosion.
And that was the reason, right from when we got the funding, or we got the yes from them, that we made this team so that it's not just us focusing on sitting on the computer and doing all the stuff, but we wanted it to be applicable and replicable both, right? So, and even when we had our first version, Mark was here and he was taking the maps out, like these maps, and talking to the farmers, and that's where the benefit is, right? So slowly, you can expand these and make the changes really happen. Yeah. Okay. All right. If there's no other questions, so lunch is already here. Both of you who are, online, you will miss that yummy lunch. And there were also some samosas. Next time when we have a workshop, so I tell you that we, our team hosts at least one workshop every year, just to show as a mode of what we did, what we learned from, whether we were doing modeling, whether we were doing monitoring, what kind of interesting stuff which we learned. And last year in November we did it on cyanobacteria, and it's not only us who were speaking, but there were experts from all over who have dedicated their lives, I would say, on these specific topics to learn from each other on any critical issue, right? So stay tuned on our website too, like whatever new workshops are coming. But yeah, at least once a year we make sure that we have a workshop to exchange what we have learned and learn from others also on these topics. Well, thank you so much for everybody who came in person and who attended the whole thing online. And like I said, everything will be shared.